Hi, I'm Marc Weiss of Marc Weiss Consulting. I'm going to talk to you about global navigation satellite systems and their use as a primary time source and about PNT, stuff like that. If you can take away two messages about GNSS from this talk, remember first that GNSS are extremely useful. The constellations are growing. They provide extremely accurate real-time UTC time and frequency, mostly for free. They are amazing for navigation and positioning. They're a huge $100 plus industry. However, the signals are dangerously vulnerable to both accidental and intentional interference. There is a family of global navigation satellite systems. The US has GPS. Historically, I think GLONASS was the second from the Soviet Union, now from Russia. Galileo from the European Union. Beidou or Compass from China. There are also regional navigational systems. Around North America, there's the Wide Area Augmentation System, or WAS. In Europe, there's EGNOS. In the Indian subcontinent, there's the Indian Regional Navigation Satellite System, or IRNSS. Also, there's GEGAN. Compass is the Chinese system, which incorporates a regional system plus a global navigation satellite system. In Japan, there's this QZSS, quasi-zenith satellite system, which augments GPS as well as the MSAS system. So there's quite a lot of systems in use as satellite systems for navigation. In the Indian system, it's now called NAVIC instead of the IRNSS. There's also GEGAN. It's the Indian version of what Japan does as QZSS. They're both based on augmenting the US GPS system. General properties. What are GNSS? What do they do? How do they work? They all provide position, navigation, and timing. You should know the acronym PNT. It's used in all kinds of places these days. They work simply by providing at least 4 timing signals that come from synchronized sources at known locations in space. So by sending these timing signals from known locations synchronized, they can be time-stamped at a receiver and used to get 4 of them, and you solve for 4 unknowns, 3 position and 1 time, either X, Y, Z, and T, or latitude, longitude, and height and time, or some other coordinate system for 3 coordinates of position, 1 of time. As the signals go through the ionosphere, they have to be calibrated for the delay so that all the systems use at least 2 frequencies, because as the signals go through the ionosphere, they're delayed proportional to the reciprocal of the frequency squared. They generally can be organized into control systems, how the global navigation satellite systems are controlled, how they operate in space, and then how users on the ground use them or augment them. They all have open and restricted services. Open means that they're free and available to use for anyone. Restricted services require special uh, subscriptions or uh, encrypted signals. All the signals are extremely weak. They're all in the noise below the ambient noise level, and they are all clustered in the L-band spectrum. The advantage of this is it allows them to operate by a single set of hardware, but on the other hand, it makes it relatively easy to attack the signals because they're clustered in the L-band spectrum. So what are the error sources of time from GNSS? So if you see the arrow coming from the satellite in space, the first problem is there are errors in the knowledge of the accuracy of time or the accuracy of position. As the signal leaves the satellite, the signals travel through space, hit the ionosphere where they are delayed and inhibited by the iono and tropospheres, ionosphere and troposphere. They then come near the receiver where the receiver needs to have good coordinates in order to accurately know what position you're in. There can be multipath interference as the signals bounce around off buildings or off the ground. They can be jammed and spoofed, which are generally intentional sources of error. You also need to know delays in cables, the delay through the receiver, and the receiver software can cause problems. How do you get time from GNSS? Time signals are the basis of positioning. All the positioning and navigation signals use time stamping as the basis for their operation. The clocks on the satellite vehicles, the SVs, are free running. In order to get accuracy for position or time, the data are uploaded from the ground and the positions and time are predicted. For GPS, the predictions are about once per day. And so the positions are needed to know the delay from the satellite to the receiver, as well as to solve for the receiver positions. Now, if you're getting time or frequency from GNSS, the receiver is a system. Besides the GNSS receiver, there's also a local oscillator, which can be a quartz crystal oscillator, perhaps a crystal that's better, an oscillator that's better than the crystal in the GNSS receiver, such as an oven-controlled crystal oscillator, or it could be an atomic oscillator, such as a rubidium vapor cell. This chart shows the spectra of the signals from the global navigation satellite systems. The top row is for the GPS signal. It shows on the left the open civilian signal. In the middle, the M code, the military signal, and on the right, a combination of commercial and military signals. The next two rows are the GLONASS system from Russia. The next row is the Galileo system from the European Union. The next two rows are the signals from the COMPASS signal system. And then below that are the regional systems and the spectra of them. What I'd like to emphasize is that the primary signal, often required to lock on any of the other signals, often a system has to lock on GPS before to lock on any of the other satellite systems. So this makes them all more vulnerable. So now I'm going to say a few words about the vulnerability of global navigation satellite systems. I like to say that the best feature and the worst problem is that GNSS are extremely reliable. Why is that a problem? It's a problem because it can lead users to not use backup systems. The jamming power required to jam a signal at the GNSS antenna is on the order of a picowatt. That's a thousandth of a billionth of a watt. There are many jammer models, from so-called personal privacy devices, which are generally illegal but can be bought online simply by looking them up. These are like a jammer that you can plug into the lighter on your vehicle. They're often used by people that don't want to be tracked, either thieves that are stealing cars, or criminals, using vehicles for the drugs, or they can be as intense as military jammers. I believe North Korea jams South Korea regularly. Second kind of general intentional form of interference is spoofing or meconning. What is spoofing? Well, the signal comes down from the satellite and it is in the ambient noise level. In order to see the signal at all, the receiver has to generate a code that matches the known code from the satellite. That explains why some of the signals are free and open and others can be controlled carefully, because you've got to know the code that the signal is using from the satellite. And for the military signals, these codes are secret. For the publicly available signals, the codes are very well known and they're short, and they can be spoofed by uh, uh, locally generating exactly the same code, matching exactly the way the satellite is transmitting it, so that it arrives at the antenna coincidentally with a signal from the satellite. Then you increase the power of this locally generated code, and you pull off and control the receiver. So the receiver doesn't know which is the real code and which is the fake code, the counterfeit code, and you can either make the receiver have the wrong time or frequency, or even the wrong position. You can tell the receiver that the user's receiver is anywhere in the world or on the moon or anywhere, and the receiver, if it doesn't have the ability to detect or is not looking for some kind of spoofing, will simply follow that. There's several kinds of spoofing, as I've shown on this slide. There's meconning, which is simply a delay and rebroadcast, or there are more complex ones, as I show in the slide. You can simply have a signal simulator and use that. You can have something more complex defined by a software radio, software defined radio, or SDR. There are very sophisticated spoofers that coordinate multi-phase lock spoofers, and can be very expensive, using systems from military systems. Here's an example from GPS World in April of 2020, so-called circle spoofing in Tehran, where receivers were made to believe that they were simply going in a circle around Tehran. Thank you for your attention. I would emphasize that global navigation satellite systems are extremely accurate, extremely reliable. This can be perhaps their greatest advantage and disadvantage.